All right, everyone, welcome to our second review for exam number 1, which is coming up this evening. So I guess without further ado, why don't we just go ahead and get to the questions here. I'm going to do the kind of the same format that we did previously, where I do maybe 3 questions from the people in the chat, and then 1 question from our audience. So I think I'll probably do that. And try to avoid asking the same question. Oh, wait, is this not working? Can you not hear me? Can you not hear me? Okay, you can hear me? Wonderful. All right. Yeah, so also be sure try not to ask a question that was asked last time, because I already put the video up for that stuff. All right, chat. So it's time for you guys to spam whatever question you want. So go ahead and do that while I open up my internet here. What? No. Why did it X out of that? Remember, only say it once. No cheating. No like having the same person spam. Oh my God, 2-factor authentication is the worst. Yeah, the other week I switched my phone and I had to like call into IT in order to get access to Canvas, and it was annoying. Okay, calculus 2. All right. Let's see here. What do we got so far? Practice exam 6, 14, 16, 17, 14, 6. Lots of practice exam. Let's see here. I think I see a fair amount of practice exam 14. I think that one might be the winner by a little bit. So let's take a look at that one. Let's see. We have a physical 4-function calculator. Can we use it? No, you can only use the 1 and R1. The only physical objects you're allowed to have with you on the exam are the scratch paper, your writing utensil, and your ID. Let's see, let's go to practice exam 14. Okay, so this one wants us to find a volume right here. Okay. Oh, so let's, yeah, sorry, let me get rid of this for the live people. There we go. All right, so this one has a region between 0, x equals 1, y is e to the x, and y is negative e to the x. We didn't do this one last time, did we? Does this look familiar? Okay. All right. So we have this, and so this is the region for our base. All right, now the cross sections for this object are perpendicular to the x-axis. And what shape are they going to be? They're going to be equilateral triangles. Okay, so as always, let's draw a picture. So here's our axes. Here's x equals 0, which is the y-axis here. And then we have x equals 1. Let's say maybe that's right here. We have y equals e to the x, which looks like this. It's the exponential function. And then we have y is negative e to the x, which is simply the negative version of what we have up there. All right, so this is our region here, and we have cross sections perpendicular to the x-axis, and they're in the shape of equilateral triangles. So we kind of have these triangles that are popping out of the page here. And what the shape is going to look like is it's going to have this big ridge going down the middle, and it's going to have these flat sides right here. All right, now we need to find out what the volume of this shape is going to be. And as always, the way we're going to do that is we're going to figure out the volume of a slice and then add them all up. Okay, so the volume of one slice. Well, the volume of one slice is how thick it is times the area of a triangle. So if we have 1/2 base times height, and then we have times dx. All right, now let's see here. We need to come up with a good way of expressing the base and the height of this equilateral triangle right here. All right, so let's take a look at our picture. What do you guys think a good name for the distance from here to here is going to be? What's this distance? It's going to be y, right? This is the distance from the axis vertically up to our function. So that's going to be y. And in the same way, this distance, since it's symmetric, will be exactly the same thing. So it looks like our base is equal to 2 times y. So we have 1/2 times 2y. We have whatever the height is, and then we have dx. All right, now we need to figure out what the height is. And this is going to rely on the fact that we're an equilateral triangle. So let's draw this picture here. Here's the equilateral triangle. Let's say that all of the sides are going to be length 2, for example. And we want to know what the height of this is going to be. Does anyone happen to know the height of an equilateral triangle where all the sides are 2? Does anyone know what that is? Square root of 3, absolutely. Now, for those of you who didn't know, don't worry. How are we going to figure this out? Well, this line right here represents the height. It cuts the triangle in half, right? That means that this is 1 and this is 1. So if we wanted to know the height, we could do 1 squared plus the height squared is 2 squared. So the height squared is 3, meaning the height is the square root of 3. So you could either kind of just have that fact memorized about equilateral triangles if you have that memorized, or you could figure it out with the Pythagorean theorem right here. All right, now that means that if all of these are 2y instead, then this will be root 3y. So our height is square root of 3 times y. All right, so far we have 1/2 times 2y times root 3y times dx, which is going to be root 3y squared dx. Now the problem is that we don't have x's in here. We have a y squared. So what's the thing we usually do about that? How are we going to fix this problem? Y squared. Oh yeah, we're going to use y equals e to the x. That's right. So since we know that y is e to the x, or we could have also used negative e to the x, we have root 3 e to the x squared, which will be root 3 e to the 2x dx. Why was it square root of root 3y? It's because it's an equilateral triangle. So we have 2, 2, 2 right here. If we cut it in half, these are side length 1, and then we did the Pythagorean theorem to get root 3 right here. All right. So let's see here. So we have root 3 e to the 2x dx. And so now what we're going to do is we're going to throw it into an integral, and we get the whole thing. All right. So let's see here. Now we need to know the bounds of our integration. Remember, we're integrating with respect to x. So we're looking for the lowest and highest x values that we have for our shape. So what's the lowest x value that we're going to have here? Yeah, it's going to be 0, right? And then the highest x value, which is over here, is going to be 1. All right, now I'm just ready to integrate here. And this is thankfully a Calc 1 integral. What I'm going to do is I'm going to divide by the coefficient of e to the 2x here. So I have root 3 over 2 e to the 2x from 0 to 1. and then I plug in 1 and 0. So if I plug 1 into here, I get e squared, and I subtract, and then I plug 0 into here, e to the 0 is going to be 1. So I end up getting root 3 over 2 times e squared minus 1, which is kind of a strange number, but that ends up being our volume here. How do we know it was dx at the start? Whenever they say it's perpendicular to whatever axis, whatever this variable is going to be our d, whatever it is. How did I find the bounds? So I'm integrating with respect to x, right? And the lowest x value this shape takes on is 0, and the highest x value it takes on is 1 right here. Why'd you attach a y to the square root of 3? Well, because the base is 2y. So normally if we have 2, 2, 2, this would be root 3. So if we have 2y, 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 this will be root 3y right here. All right, wonderful. So we got that one. That's the first chat question. What are we going to have next? What is our next question? Oh yeah, we have a question about this in the audience. Yeah. Oh, yeah. So if you happen to know the area formula for an equilateral triangle, then yeah, absolutely. You can totally do that. All right. Let's see here. Yeah, however you could find the area is it's fine. All right, so we have 16, 18, 15, 18, 16, 4, 6. I think I did 16 in class. Did I do 16 in class? I did 7. Oh, okay. Okay, 16.
Wait, I'm sorry. How'd you get like how do you plug in like e to the x for the y's again? Like I don't understand.
So I want to know how long this is, right? So I know the distance from my axis to the curve is y, right? So then that means this whole base is 2y.
Okay.
But then once I go through all of this right here, I remember that y, what is y equal to? It's e to the x. So that I just substitute x in there.
But negative e to the, oh wait, that's just I guess.
Yeah,
It's the
you
same
could do that as
distance.
well, and then you would just square the negative away.
Okay. And then oh wait, never mind.
All right, let's see. Okay, seems like we have a high demand for looks like 16. Let's go ahead and do 16 right here. Actually, honestly, 16 is going to take like probably the rest of the class, if I'm being real with you. And I'll also be real with you. The fluid pressure problem probably won't be this difficult in the exam. I mean, do you guys still want to do this, or would you rather do a different one? Yes, no, no, yes, no, no. I'm not saying that you won't have like a circle or something, but it won't be as bad as that one. Okay, well, we'll do a different one. Okay, that's yeah. So the audience has a good compromise. Can you at least maybe just set it up, or like just walk us through it? Yeah, I could do that. That sounds like a good compromise because we can at least think about how to do these problems. All right, that was a good idea. All right. Okay. So this will be like a summary of problem 16. So find the force due to pressure on a circular plate of radius 3 whose top just touches the surface of the liquid. Okay, so the first thing we should do for any of these problems, and I keep saying it over and over and over again, is we need to draw a picture. For any application problem or any volume problem, we should draw a picture. So here's the surface of our water, and we have a circular plate of radius 3 that just barely touches the surface of the water right here. All right, so this is radius 3, and we want to find the pressure on this right here. Okay, so let's see. So as always, our force due to pressure is rho GHA. And the way we're going to do this is we're going to find the force due to pressure on little slices of our circle, and we're going to add them all together. So by slices, I mean rectangular slices, and they're always rectangular slices, no matter what. They're always going to be rectangles. Even though this shape is a circle, we're still using rectangular slices no matter what. All right, so rho and g are constants, and all of our answers have rho and g in them, so we don't really care too much about those. H is the depth, and as long as we set h equal to 0 and increasing downwards here, then we're good to go with the depth. So usually what we have to figure out for these problems is what A is going to be. And since we're finding the area of a rectangle, it's going to be the width times the height. And what do you think I'm going to call the height of this rectangle? So it's a very tiny distance in the h direction. So I'm going to call this one dh right here. All right, so all these problems boil down to is figuring out what your width is. And W of h depends on the shape of the object. So for example, if you have lines on the outside, like maybe it's a triangle or a trapezoid or something like that, then you're going to set up a line equation. If you have a circle on the outside here, you're going to use a circle equation. So whatever shape is on the outside here that's bounding your rectangle right here, we're going to use whatever formula for that shape is. Would this be different if it were 5 meters under the surface? Nothing so far would be different, but setting up our width function and our bounds would be different if we were 5 meters below. All right, so we want to come up with a width function, and we have a boundary of a circle, so we want to get the equation of a circle. So why not the equation of this circle right here? I mean, this is the object after all. So I'm going to draw my axes like this. I'm going to call this maybe the x-axis. And then we already have a vertical variable, h, so I'm just going to use that. So this going downwards would be the h-axis. Now I want the equation of this circle with x and h. So this is a circle of radius 3, right? So the radius is 3. Now, in terms of x and h, what is the center of this circle going to be? You guys see what it's going to be here? 0, 3 is right. So remember, h increases downwards. So this is actually going to be positive 3 right here. When we go downwards, remember, we set h to be the depth. So it's going to have a depth of 3 and then a horizontal distance of 0 because we just put the axis right here. All right, so we have a circle of radius 3 and center this. So then that means, sorry, let me shift my papers here, that our equation for the circle is going to be x squared plus h minus 3 squared is 3 squared, or 9. All right, and then what I'm supposed to do is I'm supposed to find the width, right? So far, it seems like none of this has to do with the width of this. Well, let's see if we can come up with a relationship for the width to what we have. So what is this distance going to be right here? The horizontal distance from our axis to the curve. It's going to be x. That's right. And then if we go this way, this distance is also x. It's the same distance. And since I'm doing distance, I'm not going to call it negative x. It's still a distance of positive x. So that means my width across the entire thing is 2 times whatever x is. So if I could solve for x here and get what it is, I just multiply that by 2, and then I have my width, which is my main goal for setting up this integral. All right, so let's see here. So I'm going to have x squared is 9 minus h minus 3 squared. I have x is going to be the square root of this. I'm going to pick the positive square root because we're doing distances here. And then I'm going to double this to get w. So there we go. We were able to find w from all this. So we could take that and put it in here. So our force on each slice will be rho g h and then 2 times the square root of 9 minus h minus 3 squared dh right here. Why did I use WH/DH? Well, the H right here, this is part of the formula for the force here. Oh, W of H, it means it's a function of H. It depends on H. I think that might be what you're asking about. So it's W of H because it depends on H. All right.
Dr. Manley.
Yeah, what's up?
There was a question on Chronos for, I think it was the rocket problem, which was number 4. And to get the right answer for that, you didn't end up multiplying like the area with an H. And so like, what's the difference between that problem and the rest of the problems where you do have to multiply it by that H to get that like length value, I think?
Well, that problem wasn't computing a force. That problem was computing work, which has an entirely different formula. This H right here, this comes from this being force due to pressure. So that this is definitely going to be a much different problem from that rocket one. Maybe we could do that later if that's of popular demand. We could take a look at that.
So just for clarification, with work problems, we may not necessarily have to add that H in there, but for force problems, we do.
This H, yeah, because this H is inherent in the formula. So you always have to have the H in here for the pressure ones. But for work, yeah, it really depends on what the problem is.
Okay, thank you.
All right, so now that we have this, we have the force on one slice, then we integrate everything, and we get the force on the whole deal. All right, and then I want to do one final thing, and then I'll just stop the problem here because the rest of it is about integrating this. Most of these problems have nice integrals. This is like the notable exception here. What would the bounds of this integral be here? You guys know what the bounds of this integral would be? 0 to 6. You guys are getting good at this. That's right. 0 to 6. And remember, the idea behind the bounds is it's wherever the object is. So the object begins at a depth of 0, and then we go down 2 radius lengths to the bottom, which will be 6 right here. Absolutely. Then you would have to do this integral. And for most of these problems, it ends up being a polynomial integral, but this is an exception. This one you would probably do, you could do a trig sub for this, or you could use some of those special techniques I talked about in class that one day, where we use the fact that part of this can turn into an odd function, or we use the area of a circle. It's up to you which one you want to use right here. But I'm not going to spend time talking about that because that's a very specific case right here. All right, I want to have one more question from the chat here. So what's chat's last question before we move to the live audience? All right, example 9 and 18. Anything with work? A rocket problem. If it was 5 meters under already, would the bounds be 5 to 11? Yes, they would be. Looking at this, I think I see probably the most demand for 18. I think 18 is probably the one that has the most demand. So let's take a look at that one. All right, so 18 is just a straight up integral right here. So let's see here. We have the integral of x divided by x squared plus 2x plus 2 to the 3/2 dx right here. All right, so let's go ahead and try this one here. So let's see here. I see a 3/2 power, which immediately tells me that we can't do partial fractions for this. This partial fractions only works if we have non-fractional powers or whole number powers. So we can't do that, but I do see a quadratic in here. And that makes me think, okay, I have a quadratic and then I have this 1/2 power here that's kind of there. What I'm going to do is I'm going to try trig sub here. Now, this would be good for trig sub if there weren't that annoying 2x in here. So what was the way that we learned to deal with that? How do we deal with this middle term if we still want to do trig sub? We complete the square, that's right. Let's see. So if we try to complete the square here, we divide this number by 2 and get 1, and then we square 1 and get, well, 1. So I add and subtract 1. All right. And then x squared plus 2x plus 1 right here is x plus 1 squared. And then I have -1 plus 2 will be plus 1. So there we go. So we managed to complete the square for this. And now what we're going to do is we're going to, oh, this is to the 3/2. Almost forgot that. There we go. Now we're ready to do our trig sub right here. All right, so let's see. So we have a variable squared plus a number squared. Which trig function are we going to use in this case? Tangent is correct. So we're going to have x plus 1 is tangent of theta. Remember, we have the square root of this number in front of tangent, and whatever the variable thing is being squared, that will equal our trig function. Now, one of the easiest things to forget is to include the differential here. So if we do the derivative of both sides, we have secant squared of theta d theta right here. All right, so let's see here. Let's go ahead and substitute in everything. All right, so I have x plus 1 squared is tangent squared, and then I have plus 1 to the 3/2. Now up here, here's where things get a little bit messy. I have an x, right? But here I have x plus 1 is tangent, but that's not too hard of an issue to deal with. I could just say that x is tangent of theta minus 1. So tangent of theta minus 1 up here, and then I have dx is secant squared of theta d theta. All right. Why is it just x plus 1 equals tangent of theta? It's whatever the variable thing is being squared, that's on one side of the equal sign, and then the trig function times the square root of this number will be on the other side of the equal sign. And the reason why it ends up working and why it's helpful for us is because this is a Pythagorean identity. What does the stuff inside the 3/2 power turn into? It's going to turn into secant squared, right? So we have the integral of tangent of theta minus 1, secant squared of theta d theta, divided by secant squared to the 3/2. All right, now what's going to happen next? Well, I have a square and I have a square root. So those will go away. So effectively on the bottom, I have a secant cubed, right? And then how is that going to cancel with the top? Well, I have secant squared go away here, and I have all but one secant go away down there. So when everything settles here, what do we have? We have tangent of theta minus 1 over secant of theta d theta right here, once we're done with all that simplifying there. All right, now what I'm going to do is I'm going to split up the fraction here. Okay, so tangent of theta divided by secant of theta. Does anyone know what that's going to simplify into? What do we get for that? Yeah, that's right. We are going to end up getting sine of theta from that. Reason being is that tangent is sine over cosine and secant is 1 over cosine. So the over cosines cancel out. Then we have 1 over secant of theta. What is that going to turn into? Cosine of theta. Absolutely right. All right, and then now we have an integral we could have done in Calc 1. So this is the good news. So the integral of sine of theta is negative cosine of theta. The integral of negative cosine of theta is negative sine of theta. And we've completed an integral, so we put a plus c there. Now, they gave us a problem with x's in it, so rightfully we should give them a solution with x's as well. And how do we do that? Well, this is where we use the triangle. So we know that x plus 1 over 1 is tangent of theta, right? So what we can do is we can construct a triangle here. So the opposite side, tangent is opposite over adjacent. The opposite side is x plus 1, and the adjacent side is 1 right here. All right, now I'm going to use the Pythagorean theorem to get this. 1 squared plus x plus 1 squared is the hypotenuse squared. So then I just take the square root. So I have x plus 1 squared plus 1 is the hypotenuse. So that's going to be our missing side here. And as always, we can go back to our original integral and see that we had something that looked like that here. So that means that we're on the right track here. We should have seen this before. Now we need to know what sine and cosine are. So sine of theta is opposite over hypotenuse. So my opposite side is x plus 1, and my hypotenuse is the square root of x plus 1 squared plus 1. All right, that's sine. Let's take a look at cosine. Cosine is adjacent over hypotenuse. So we have 1 over this. All right. So now that we have all of those, what we can do is pull a negative out of these. And then sine plus cosine, since they actually have the same denominator, we can add their numerators together. We have negative x plus 2 over the square root. And there we go. There's our answer right there. Could you do u sub instead and set u equal to x plus 1? Let's see here. Then your du would be 2x plus 2. So you could go that route and add and subtract 2 here, but eventually you're going to need to do some kind of a trig sub thing in the long run. So you could have started with u sub, that would have been fine, but you can't avoid trig sub for this one here. All right. Let's see here. So we managed to get this one. All right, now it's time for the audience to have a question. So let's see. Yeah, what's your question? Practice exam number 5. Let's see. Okay. Find the volume of the shape by rotating the region e to the x, x is 0 and x is 1 around the x-axis. All right. Okay, so let's see. So we have y is e to the x. We have y is x is 0, and x is 1. And we're revolving this around the x-axis here. All right, so let's take a look at this right here. So as always, we're going to draw our picture. So let's see, y equals x looks like this. Y equals e to the x looks something like this. And then we start this at x equals 0, and we stop it at x equals 1. So it looks like this area right here is going to be what we're spinning around the x-axis right here. All right, so let's set up our integral here. Now we have functions of x that are going around the x-axis. So does that mean we're going to use the washer method, or are we going to use the shell method for this one? right. Yeah, the washers have it. That's right. So when the variable in the function matches the variable for the axis, we're going to use the washer method. So the washer method is where we have pi times the integral, and then we have the function further from the axis squared, and then we subtract, and then we have the function closer to the axis squared. All right, now let me ask you guys this. What are the bounds of our integral going to be here? What's the lowest x value we have here? That's right, and then the highest x value ends up being 1. All right, and then now we just need to do this integral right here. So this is e to the 2x minus x squared, from 0 to 1. All right, let's see. So we do this integral by dividing by 2. And then we raise this power to 3, divide by 3. And then we have this go from 0 to 1 right here. All right, so I'm going to plug 1 into here. And so we have e squared over 2. And then I subtract 1 over 3. Then I'm going to subtract this whole thing when I plug in 0. So I do minus e to the 0 over 2. And then plus, because I get a minus sign from this being the second bound, I'm going to do plus 0 over 3. But that's just not going to be there. All right, and then we end up getting pi, and then we have e squared over 2 minus, let's see, if we do a third minus a half, that's 5 over 6. So there we go. There is our volume for this one right here. When is the bound in terms of y? When they give you functions of y. So if they were like, oh, x is e to the y, or x is sine of y or something, then you would be more likely to do a y integral. And in that case, you'd want your bounds to be the biggest and smallest y values that you would have. All right, so let's see here. So that was our audience question. Let's go back to chat now. Let's see what's going on in the chat. I see some for practice exams, 6 or 9. By the way, these questions don't need to be specific problems. They could just be general questions too. I've seen some people ask general questions, so those are also allowed. Let's see here. One thing I want to address real quickly is Christine's question. How do you know when to use y, and how do you know you need to use the total height minus y? Most of the time, you're just going to use y. If there's already a coordinate system in place, like they give you a function like y equals x squared or something, then you use the total height minus y for that. So, but most of the time, you're just going to use y or h or whatever variable you have. I just want to get that out of the way. Let's see here. I'm seeing a fair amount of requests for number 9. Let's see. Oh, how do you identify an improper integral? That's one I can answer almost instantly. So if you have an infinity as one of your bounds, that's automatically an improper integral. If one of your bounds is makes the function undefined, like for example, if we have like the integral from 1/2 to 1 over x minus 1, this would be improper because this bound makes this function be undefined. That'd be the other type of improper integral right here. All right, it looks like number 9 from the practice exam has it. So let's go ahead and take a look at that one. And I think we'll have time at least for one more question after this. So don't worry if your question hasn't been answered yet. Okay, so number 9 from the practice exam is the integral of arc sine of 1 over x dx. Okay, so we just have one weird function on its own and we need to integrate it. So which technique do you think we should use if we just have one strange function on its own and nothing really to u sub off of or anything like that? Integration by parts is right. So we're going to do IBP for this one. And I always recommend doing integration by parts whenever you have just one bizarre function, kind of just there. If you don't really know what to do, you just have one function, just this right there. You don't, it's kind of strange looking, like arc sine of 1 over x. Just try to do integration by parts. Now, how are we going to do this? Well, we're going to make u be the whole thing. And then we're going to have dv be just the dx. Because even though we can't automatically do the integral of arc sine of 1 over x, we are able to do the derivative of it. So let's remind ourselves what the derivative of arc sine is. The derivative of arc sine of something is 1 over the square root of 1 minus x squared. All right, so that means if I want to do the derivative of arc sine of 1 over x, then we're going to have 1 over the square root of 1 minus. Now, instead of x, I have this in here, so I'm going to square that instead. Then, by the chain rule, I need to multiply by the derivative of my inside. And what's the derivative of my inside here? What's the derivative of this? Oh, some people are thinking the antiderivative. Remember, the derivative, we just do the power rule. That's right. It's going to be negative 1 over x squared. All right. And then when we have dv is dx, that means that v is going to end up being x right here. All right. Now we're ready to put everything together. So we're going to have u times v. So that's x arc sine of 1 over x minus the integral of v du. But we're subtracting a negative right here. So that's going to end up making things positive. And then we have x square root of 1 minus 1 over x squared. And then we have x squared. Okay, the first thing that happens is that this x cancels out with one of the x's down there. So we're really looking at the integral of 1 over the square root of 1 minus x squared, like that. Now, what I'm going to do to make things look a little bit nicer, since we have a compound fraction and a square root there, is I'm going to multiply the x into the square root. So I'm going to move the x into the square root here. So does anyone know what's going to happen to that x when I move it in there? What is it going to become when I move it into the square root? It's going to become x squared. That's right. So when I move inside the square root, this will be an x squared. Then x squared times 1 minus 1 over x squared will be x squared minus 1. So we're actually able to tidy that up pretty nicely. We ended up getting this right here. Okay, so now our problem becomes that we need to integrate 1 over the square root of x squared minus 1. What method should we use to do that? Does anyone know what method might be good here? See a trig sub. Yeah, that's right. We're going to use trig sub here. All right, so we have a variable squared minus a number squared, right? So which trig function are we going to use? We're going to use secant. That's right. So x is going to be secant of theta, meaning that dx will be secant of theta, tangent of theta, d theta, right here. All right. What I'm going to do now is I'm just going to replace this with a squiggle, because we're pretty much just going to carry that to the end, and it's not really going to be involved in our calculations anymore. So we have the extra stuff in the front, and then we have dx, which is secant of theta, tangent of theta, divided by the square root of secant squared minus 1. Okay, now the whole point of trig sub in any situation is to exploit a Pythagorean identity. And this one right here will turn into tangent squared of theta right here. All right, so I have the square root of tangent squared. The square root and the tangent will go away, giving me just a regular tangent right here. All right, and then we have tangent over tangent right here. Those will all cancel out. So we have our stuff from earlier plus the integral of secant of theta. And thankfully, we end up back where we started right here. Or not where we started. We end up with a Calc 1 integral right here. Okay, so the integral of secant of theta is natural log of absolute value of secant of theta plus tangent of theta, and then we have plus c. All right, so now we need to use our triangle to convert things back. So let's do that over here maybe. X over 1 is secant of theta. So we have secant of theta is going to be hypotenuse over adjacent. So if we use the Pythagorean theorem to finish this off, we have root x squared minus 1 right here. And as always, we want to make sure that we've seen this before, and we really have seen this. It appears back here. All right, and then now we're ready to assemble the final trig function we need, which is tangent of theta. Tangent is going to be opposite over adjacent, or the square root of x squared minus 1 right here. All right, so then finally, let's write out what we have, and this is where we can return this to its former glory as x arc sine of 1 over x. And then we have natural log of absolute value of secant of theta, which is just an x, plus tangent of theta, which is the square root of x squared minus 1. And there we go. There is our integral right here. Where did the x squared go from the denominator? Let's see here. So we had an x squared here. One of the x's canceled with the v that was an x up there. The other x multiplied into the square root and became root x squared minus 1 right here. That's the story of this x squared right there. All right. Is there a limit on a scratch paper you get? No, you could have like a whole, as long as you could show it to the camera, you don't have any limit on it. Yeah. Let's see. So yeah, you could have done that. So 1 over x is sine of theta. But then you would have this differential to worry about. So you'd have like negative 1 over x squared dx is cosine of theta d theta. So as long as you're willing to deal with that, then you could try it that way. Let's see here. We only have a few minutes left. I really I saw a lot of demand for kind of giving a general outline of how work problems work. That's kind of fun. So I'm just going to do that now. Okay, work problems. Here's kind of a general way of doing this. And this is very general because each work problem is somewhat different right here. So the first step, actually, let me ask you guys what the first step is. It's the first thing that I do every single time we get one of these problems. What's the first thing I'm going to say? Draw a picture. That's right. We're going to draw a picture. It'll be extremely helpful to draw a picture. Once we draw a picture, then what we're going to do is we're going to divide the object into slices. So we're going to kind of cut up the slices, and what shape the slice is depends on what the problem is. So if you have some kind of circular thing that you're pumping water out of, the slices will probably be very thin discs. Or if you have like a chain link, then what you're going to be doing is taking a very tiny length of chain. The slices definitely depend on the problem. Now, once we do that, then we compute the work for each slice. And this ends up being probably the hard part here. And I can't elaborate too much more than this because this is where the specific nature of the problem comes in. But a lot of time you're going to use given information to do this in some way. Or maybe you're going to use geometry to do this. Like you might, for example, know the volume of a very thin cylinder is pi r squared h, or something like that. So we're going to compute the work for each slice. Then we get all the variables to be the same. So for example, if we have a dh, then all variables need to be h. And then finally, put an integral sign on it. And then step 6 is when you integrate. And one thing I want to say in step 6 here, when you actually do the integral right here, is the bounds are where the object is, right here. There's all these little up arrows. If you guys do that too much, I'm not going to be able to read what you're actually trying to point out. Oh my God, there's a lot of this. Let's try to keep the pessimism to a minimum here. I was actually talking about this before class. So I think you got, in order to do well, I think one prerequisite to that is believing that you can do well. So I really want you guys to go into there optimistically. And trust me, if you guys could do all right on the practice exam, or even if you could do problems maybe a little bit easier in the practice exam, I think you guys are going to do just fine here. I don't see this being like a catastrophe or anything like that. So don't worry. I'm the type of teacher that likes to train people for the marathon iron boots, where I give people harder things for practice, and then when they get to the real thing, they're like, oh, wait a minute, that's not that bad. So don't worry. Try to keep a positive attitude here as much as you can. All right, anyways, that's kind of my summary for doing these work problems right here. And it's really these two steps that are different for each type of problem. So here I can't really give any more specific advice because I need to know what problem you're doing, but they're all the work problems are going to follow this kind of paradigm right here. All right. Anyways, so that's all the time we have here. I'm going to try to post this video as soon as I can so you guys can go over it. But anyways, yeah, best of luck on the exam. And yeah, email me if you have any questions at all. I actually have a meeting at 4 p.m. I need to get to, so I actually need to go right now. Unfortunately, I can't take any other questions here.